At this point, assuming you've selected the correct Python interpreter in the command palette and activated your environment if you're using one, we're ready to start debugging. Click on Run and Debug on the left sidebar to begin stepping through the code. When you run from Ultralytics import YOLO, this command tells Python to import the YOLO class from the Ultralytics package, making it accessible in your current script. When Python encounters this line, it searches for the Ultralytics folder in the Python path and then looks inside that folder for a _init file, also known as dunder_init for short. Here, the dunder version line sets the Ultralytics package version to 8.3.27, making this version information accessible throughout the package. After that, we use the OS library to set an environment variable, omp num_threads. If this variable isn't already set, it assigns it a default value of 1. This setting can help reduce CPU usage by limiting the number of CPU threads used, which may optimize performance in multi-threaded operations. Finally, YOLO is defined in the Ultralytics.models subfolder, so Python will look in that submodule for another dunder_init file. Let's jump there. These lines import specific model classes from separate files within the Ultralytics models directory, FastSAM, YOLO_NA for neural architecture search, RT-DTR for real-time detection transformer, and the segment anything model are imported from their respective module Python files. Each file defines a class representing a unique model architecture. We won't be covering these models in this video. YOLO and YOLO world are then imported from YOLO.py. The YOLO world class is used for real-time open vocabulary object detection, which we won't be covering in this video. Instead, we'll focus on the YOLO class. Finally, the dunder all variable controls what gets imported when using from Ultralytics.models import all, allowing only the listed model classes to be accessible while hiding other functions or variables. This line imports two objects, assets and settings. Assets refers to readily available pre-trained model assets, while settings is a configuration object containing global settings for the package. The check YOLO function is a utility that verifies whether the YOLO model and setup are correct or if the necessary prerequisites for running YOLO are met. Finally, the download function, as its name suggests, is used to download pre-trained weights programmatically from the internet. And then the dunder all declaration ensures that when you import from Ultralytics, you gain access to the main classes and functions, version information, utilities, and configurations. This makes the package's interface easier to use and cleaner by exposing only the intended public items. And then we return to our initial script. We'll step into the YOLO class, which resides inside model.py. The YOLO class inherits from the model class, meaning that YOLO is a specific type of model and will inherit all the functionality of the model class. The dunder_init method is the initializer constructor for the YOLO class and accepts 3 arguments. The path to the model file defaulting to YOLO11n.pt. An optional argument to specify the task, such as detect, segment, classify, etc. And an optional Boolean argument to control verbosity for logging or debugging. The pathlib library converts the model file path provided as a string into a path object, making it easier to work with file paths, like checking file extensions or getting the file name without the extension. The method first checks if the model file name contains -world and if it matches a valid file extension. We'll step over this in the code. If the model file is not a YOLO world model, it proceeds with the default initialization process for the YOLO model. Using the super function, it calls the dunder_init method of the parent model class, passing the 3 arguments to it. This brings us to the model.py file inside the engine folder, where the superclass model class resides. The model class serves as a base class for implementing YOLO models, unifying the API for various operations like training, validation, prediction, exporting, and benchmarking. Here are some key attributes of the model class. Callbacks. A dictionary for managing callback functions, allowing custom operations during model training and inference. Predictor, a predictor object used for making predictions with the model. Model, the core PyTorch model, an instance of nn.module. Trainer, an object responsible for training the model. CKPT, a dictionary holding checkpoint data if the model was loaded from a .pt file. CFG, configuration data if the model is loaded from a .yaml file. CKPT path, the path to the checkpoint file from which the model was loaded. Overrides, a dictionary for overriding the default configuration. Metrics, training and validation metrics that track model performance. Session, an instance of a training session on Ultralytics Hub, if applicable. And task, the specific task the model is trained for example, object detection. And finally here, model is the name of the model. This check determines whether the model string represents a model hosted on Ultralytics Hub, a platform for model storage, training, and deployment. Since our model is a file name, not a hub model, we'll proceed to the next step in the code. Next, it checks whether the model is designed for the Triton server, which is used for running inference with the NVIDIA Triton Inference Server, formerly Tensor RT Inference Server. Since this doesn't apply to us, we'll step over this as well. We're also not creating a new YOLO model from scratch with a YAML file, so we'll skip that part. Instead, we'll call the _load method. The underscore at the beginning of a method name usually indicates that the method is intended for internal use within the class or module. This is a Python convention, not an enforced rule, signaling that these methods are meant as private or helper methods and aren't part of the public API. The _load method is designed to load a YOLO model from either a local or remote file, typically a checkpoint or weights file. Let's break down its components step by step. First, it checks if the weights are from a remote source. Since our weights don't match any of those remote formats, we'll skip this check. Next, if the file suffix, for example, pt, is missing, it adds the appropriate suffix to the weights file. In our case, we already have the suffix. Since we have a PyTorch model with apt extension, we'll step into this section. Next, we call the attempt load one-weight function, which resides in tasks.py inside the nn folder for neural networks. Then we jump into the torch safe load function, also located in this same file. The check suffix function will verify whether we have a valid file extension, which we do, so we can continue. Next, we call the attempt download asset function from downloads.py in the utils folder. This function is designed to download a file from a specified GitHub repository release if the file is not found locally. The file variable is converted into a string processed by check file name to ensure the file name is in a valid format, and then turned into a path object with any stray quotes removed. The function first checks if the file exists locally using path.exists. If the file is found, it returns the file path as a string. Otherwise, if the file is missing locally, it proceeds to download the file from a GitHub release. Luckily, since I already had a PyTorch file downloaded while recording, we will skip any remote downloads. But feel free to check those steps on your own if you're interested. So for now, we will just return the file path as a string. This code uses a feature called temporary modules, which sets up temporary shortcuts or substitutions for certain pieces of code to make sure an old YOLO model file can still work, even if parts of the YOLO library have been renamed or moved around. It's a way to speak the language of older YOLO models so they load correctly, even if they use outdated references. This helps the current version of YOLO work with files made by previous versions. So for example, if you see a reference to Ultralytics YOLO utils, an old location, treat it as if it's pointing to Ultralytics utils, the new location. Or if you encounter Ultralytics NN modules block silence in the model, replace it with torch NN identity, a built-in simple substitute. These substitutions only apply within the with block, making them active just for the model loading process. Save only is set to false, so we'll step over that. Now here we have the torch.load function, which loads a saved PyTorch model from the specified file. The map location argument ensures the model loads onto the CPU, regardless of where it was originally saved. This is especially useful if the model was trained on a GPU, which is likely the case, but is being loaded on a machine without one, preventing errors that could arise if the model tried to load onto an unavailable GPU. Next, we'll jump into the torch.load function found in patches.py within the utils folder. This code here makes torch.load forward compatible with newer PyTorch versions by proactively handling the waits only argument introduced in PyTorch 1.13 and required in PyTorch 2.0 and above to avoid warnings. So we return the loaded model to where we call it from, and when we run this line, ckpt becomes a dictionary. The ckpt file contains a snapshot of the model's training state, including several key components, metadata, stores the date, version, license, and links to the framework documentation. Model architecture contains a complete outline of the model structure, classes, and layers. Training configuration specifies key training parameters such as task type detect, training mode, model configuration, YAML file, COCO dataset path, number of training epochs, batch size, image size, and early stopping criteria. The ckpt file is invaluable for resuming training or analyzing the model's performance, since it saves both the architecture and the current training state at that specific checkpoint. We skip over this step since ckpt is a dictionary, and we return ckpt and the file to the attempt load one wait function in tasks which called it. Now we have both the ckpt and the waits ready. This line of code merges two dictionaries, the default configuration settings from default configuration dictionary and model-specific training arguments from the checkpoint ckpt.getTraining arguments. If the model-specific training arguments exist, as in this case, they take precedence over the default settings, ensuring the model resumes with the correct configurations used during its original training. This line of code retrieves the model weights from the checkpoint ckpt using the EMA exponential moving average model if available, or the regular model weights if not. It then moves the model to the appropriate device and ensures the model's data type is in 32-bit floating point format, FP32. The underscore apply method is inside the base model class and applies the function fn to specific parts of the model, particularly the detection head detect class. It modifies certain attributes of the detection head, such as stride, anchors, and strides, using the provided function fn. This ensures that the function is applied selectively to the right parts of the model, keeping the changes targeted and efficient. We will return and step into the underscore apply function again. The reason we invoke the method twice is that the first time it happens when we call .toDevice, which moves the tensors to the specified device. The second time occurs when we call .float, which converts the model's tensors to 32-bit floating point format. Both operations require the underscore apply to ensure the changes are applied to the model's tensors correctly. This line rebuilds model.args by creating a new dictionary that only includes key value pairs from args where the key exists in default configuration keys. This ensures that model.args contains a controlled set of configuration values relevant to the model, prioritizing those specific keys. Any previous values in model.args are replaced with this new filtered dictionary containing only the essential configuration parameters expected for this model. Here we simply assign the specific string, in this case YOLO11n.pt to model.pt path. We will step into the guessModel task function, where we first check if the model is an instance of nn.module PyTorch model. Then we attempt to extract the task key from different locations within the model's configuration. The function will evaluate several potential paths, and in this case, it will return the detect value as the task type. Our model already has the stride attribute, so we will skip this step. If the attribute were missing, however, we would create it and set its value to 32. While our model does have the fuse method, the fuse boolean is set to false, so we skip the fusing of the convolution and batch normalization layers, at least for now, and directly set the model to evaluation mode. Setting it to evaluation mode is crucial because it ensures that layers like dropout and batch normalization behave correctly. These layers function differently during training, where dropout is active and batch normalization adapts, versus in evaluation, where dropout is disabled and batch statistics are used. This loop iterates through all layers in the model to refine its behavior and ensure compatibility. It updates each module's in-place attribute to control memory usage, enabling in-place operations, modifying data directly without making a copy for greater efficiency, Additionally, it makes a compatibility adjustment for nn.upsample layers to work smoothly with PyTorch 1.11 by adding the recompute scale factor attribute even if set to none. We return model and CKPT, which initialize self.model and self.ckpt. We also set self.task by retrieving the task from the model's arguments. This line of code sets up the overrides attribute and updates model arguments to keep them in sync. It filters out unnecessary settings, retaining only key ones like image size, data, task, and single class to ensure compatibility and discarding everything else. We save additional values in self, like the path, overrides, and model name. Then we exit the underscore load function, followed by the dunder init function in model.py, and finally the dunder init function in the YOLO class. This brings us back to our original YOLO11.py script.